Welcome. Let's get started. Today we're going to be talking about integrating rational functions. So a rational function is something that looks like a ratio of two polynomial functions. Something like this. Right? So for example, x squared plus 1 on 3x cubed plus 2. That's a rational function. We're going to discuss how to integrate rational functions. But before we get into that, I'd like to sketch briefly why you care about that, or why you will care at some point a little bit later in your career with calculus. So we've talked about this picture a few times before. So you could imagine starting with some real system, and then you model that. Modeling means choosing what to ignore, what quantities to measure. Usually those measurements are formulated as functions, and the evolution of those functional values over time are described by differential equations, or DEs. DEs are the final topic of this course, so we will get there in a bit more time. Once you've formulated a model of your system as a DE, you can attempt to solve it. And once you've solved the DE, you can predict and therefore hopefully control the system of interest. And what we're talking about today fits in this step. In a way that we won't have time to fully explore in this course, but you'll see more of in Calc 2, solving particular natural examples of DEs gives rise to the problem of integrating rational functions. And we're going to more or less completely solve that problem today and next time. But before we do that, I have to tell you a bit more about integrating 1 over x. We've seen this formula, maybe this formula over here. We've seen this formula earlier in the course, right? And maybe you were wondering a little bit about what the content of this absolute value was. And at the time I didn't say much about it, but now I want to come back and address that now. So let me just do that on this board. All right, so the point I want to make is, let's think about antiderivatives. So for x in the interval 0 to infinity, we have that the antiderivative, the derivative of the logarithm is 1 over x. Good. For x negative, we have d dx of, well, log x doesn't even make sense, right? Because you can't feed a negative number into a logarithm. But you can make sense of this if you put a negative x here, right? Then d dx of log minus x, well, the general rule is that if you differentiate logarithm of something, you take the derivative of what's inside and put it up the top. That's minus 1 divided by the original thing. So that's 1 over x. Okay. So what does that tell us? Well, it tells us that wherever 1 over x is defined, so on its domain, which is R with 1 removed, d dx of logarithm of the absolute value of x is equal to 1 over x. That's what these two results combined tell us. All right, so that's what this is saying. Right, that's what this is saying. Now the thing to keep in mind is that this kind of expression, so the integral from minus 1 to 1 of 1 over x dx, isn't allowed. Why? Well, because 1 on x is not defined at 0. You can't integrate a function over a domain that it's not defined on, at least not at this level. Okay. So the reason for that intuitively is that if you integrate from minus 1 to 1, you're going to be getting an infinite amount of area. Now you might say, well, those are infinite and of equal size, so they should cancel out or some such thing. And in this case, you're kind of lucky and you get away with that. But in general, you shouldn't be messing around with expressions like this that involve gaps in the domain of the function. Okay, so what does it mean? What does this formula mean? Well, it just tells us how to evaluate integrals which are of the form from a to b 1 over x dx, where either they're both negative or they're both positive. Right? And in either of those two cases, so that's an area that's completely on the left or completely on the right of 0, then we get, this is log absolute value of b minus log absolute value of a. So if you like, read this as two statements. One about integrating areas that are safe because they're over here, and one about integrating areas which are safe because they're over there. All right. So let's try an example. The integral of 1 over 2x minus 3 dx. So we're going to make a substitution and turn this into an integral of the form that we just studied. And I want to remark on two different ways of doing that. So let's do it the first way first. So we're going to substitute u is 2x minus 3. Then du dx is 2. And that means that the integral of 1 over 2x minus 3 dx is, so let me write this as a half du dx is 1. So this gives me, it's 1 over u, and as usual I imagine secretly there's a 1 in there, and that 1 becomes a half du dx dx, which is a half 1 over u du, which is a half log u, which is half log 2x minus 3 plus c. Okay, good. That's our answer. But we could also, if you look at this expression here, we could have factored out the 2 to begin with. So let me do that on the next board. So we start with the same integral. but we first divide by 2, and take that out. Now we do a substitution, but it's a different substitution. It is u equals x minus 3 on 2. So du dx is just 1. So that becomes half integral 1 over u du dx dx. So that's half log u plus c. That's a half log x minus 3 on 2 plus c. All right. So that and that, they're both claiming to be the integral of the same thing. But are they the same thing? So it looks a bit like an 8, doesn't it? What's the difference between those two expressions? Well, keep in mind, first of all, that the indefinite integral is not a function. It's a family of functions. So this stands for the family of functions, which is a half log 2x minus 3 plus any number. And similarly, that family over there is a half log x minus 3 on 2 plus any constant. And the thing to observe is that by the rules of logarithms, logarithm of a product is a sum. So that common factor of, well, not common, but that factor of a 2, I can take it out here and end up with something like that. All right, so that log 2 becomes, by this, I get half log 2 plus the thing I have over on the other side. And those are indeed the same thing, because they differ by a constant, right? Which means that I can absorb this constant into that c and have the same thing as I did over there. All right. So when you're integrating, don't be worried if the expressions look a little different. They may actually be the same family of functions. All right. So moving on. So we're going back now to the general problem of integrating rational functions. So we're going to talk about this. We just talked about the easiest case, right? Well, I guess the easiest case is where q is a constant and p is a polynomial. We know how to integrate that. That's the first integral we ever learned. The next easiest case is when p is 1 and q is x, and we just discussed that. Or when q is a linear, and we've just discussed that by substitution. All right, so moving on then, what's the next most complicated case? Well, that would be where p is 1 and the denominator q is a quadratic. And there's a few cases to consider. We're going to start with the case where the denominator is an irreducible quadratic. Remember, a quadratic with real coefficients, so that's presumed here. The coefficients These are real polynomials that we're integrating. There's no complex numbers in their coefficients. All right, so there's kind of an implicit relationship mentioned here between something that looks like this and something that's an irreducible quadratic. I don't want to spoil that by getting into it now, so you can somewhat ignore this slide. It's just, if we could write our denominator in this form, then recall this formula would allow us to integrate it. Okay, but I want to make the connection between these two ideas, irreducible and being able to be written in this form for some linear u. Okay, and that's the content of this slide here. So suppose we're given a quadratic, ax squared plus bx plus c. Now we can always write it as a perfect square plus a constant. That's this trick here. As I've mentioned before, I don't memorize this formula. If I want to put something in the form of a sum of squares, I just come up with the factor that matches the linear part and then make the r whatever it has to be. So that's similar here. So you factor out the a, x plus b on 2a, that'll give you, when you expand the square, will give you 2 times that. That'll be b on ax times a will give you bx, right? What is r? We'll just rearrange this equation to solve for r, and you'll find that r is c minus b squared on 4a. Okay. Now, the observation to be made is that, okay, so you can start with a quadratic with real coefficients. You can complete the square to get a remainder. That always works. Suppose you complete the square and you get here a positive number. Well, then you can set s to be the square root of r, and then this here will be s squared. This part you can call u, right? That's a linear substitution. So as long as this is positive, you can call it s squared. You can make this u squared, and the a you can just factor out, so don't worry about that. But then you're in the situation where the denominator, if this polynomial is your denominator, I guess it's a bit of a, yeah, it's a bit of a unfortunate thing that's a p, right? We're imagining this is our q that we're doing something to. I mean, this slide's about a generic polynomial, but it's just the generic polynomial has a letter that sort of appears in the context we're discussing. Okay, suppose we can complete the square and get something that looks like this. Then we're in the situation where we can use arctan to integrate it. Okay, so when does that happen? I can always assume a is positive, if necessary by factoring out a negative number. Okay, so suppose a is positive, then well, what does it mean for q to be irreducible? Q irreducible. Well, what does irreducible mean? It means it has no linear factors over r, right? Which we know in terms of the discriminant means the discriminant has to be negative. And the discriminant is b squared minus 4ac. Well, that's the same as b squared less than 4ac. A is positive, so that's the same as b squared on 4a is less than c. And that's the same as c minus b squared on 4a is positive. But that's the remainder on completing the square. Okay, so you see that q is irreducible if and only if the remainder on completing the square is positive, which means it can be written as the square of some real number s, which means that we can put it in the form to which we can apply the arctan method. All right, so let's see how that works in an example now. Okay, so let's have a look at this polynomial, x squared plus 2x plus 2. Let's complete the square. So as I said, when I complete the square, there's no a to factor out. I put here whatever 2 times that is going to end up as the coefficient of the linear part. So it's going to be a 1. Right? So when I expand that, I'll get x squared plus 2x plus 1. So I need to add a 1. Call it a 1 squared because I want to think of things as u squared plus s squared. Right? All right, so now set u equals x plus 1, du dx is 1. So the integral of 1 over x squared plus 2x plus 2 is the integral of 1 over u, not really, 1 over u squared plus 1 squared. You don't have to write 1 as 1 squared if you don't want to. It's a bit ridiculous, but I'm just trying to match the template. Times du dx, which is the integral by substitution of this, which is 1 over 1 arctan u. U was x plus 1. Okay, so you see how that worked, right? And I hope you see that that's going to work anytime you integrate 1 over qx, where the qx is irreducible. Because if it's irreducible, then it can be written as some linear thing squared plus something squared. You can take u to be the linear thing, and it'll work exactly like this with some other linear thing inside the arctan. Right, so this example does, sort of by analogy, the general case, where the denominator is irreducible. So now let's try a slightly more complicated example. So now we've got a numerator that's not 1. Okay, so we'll just reuse the notation from there. So when we look at this, we'll get u divided by u squared plus 1 du. And I'm skipping the first several steps, right? We make the same substitutions, and we'll end up after the integration by substitution step with this. Well, now what? That's not an arctan anymore. Is it an integral we recognize? Well, not immediately. So what do? Well, we make a further substitution. Right, we're just lucky, as the slide says, that the numerator is the derivative of the denominator. So let v be u squared plus 1, then dv du is 2u. So therefore, half dv du is u. So this is half dv du on v du. So integration by substitution makes this this. Well, v is u squared plus 1. But we shouldn't leave it like that, right? Because the question is about x, not about u. So what's u squared plus 1? Well, it's our original polynomial, x squared plus 2x plus 2. Okay, so before we got an arctan, and now we get a logarithm. And in fact, these two together basically handle everything in this initial part. All right. With a little bit more. So what have I done here? I've changed the numerator and I've subtracted 3 from it. So the numerator is now no longer just u, but it's not so different, right? So u is x plus 1. Therefore, x minus 2 is equal to u minus 3. So the integral is the integral of x minus 2, which is u minus 3, divided by u squared plus 1 du. So we get the integral we just did. Again, I'm skipping the initial steps, right? Because we've already done that. Minus 3 times the other integral we did. So we get this, which was a half log x squared plus 2x plus 2 minus 3 arctan u. Okay, so I hope you can kind of see how this settles the general case where you integrate something which is linear divided by irreducible quadratic. I'll just talk you through why we're now done with this case. So suppose you're given something like that. The irreducible quadratic, for the reasons I explained, can always be written as u squared plus s squared, where u is linear in x. That is, it's ax plus b for some a and b. But that means the numerator can be written as a linear function of u. So it's cu plus d for some c and d. But then the first term, which looks like u divided by u squared plus s squared, will give rise to a logarithm. And the second term, which looks like 1 divided by u squared plus s squared, gives you an arctan. So the numbers will be different, but the general case of linear divided by irreducible quadratic will go exactly like this. So we're now done with this case. Example 4.22 has a comment about funny coefficients. It's actually not adding anything to the discussion. It's just a disclaimer that if you see somewhat nasty looking numbers turn up in these examples, don't be scared. That's kind of a comment more on the difficulty of preparing examples which are artificially easy in terms of the numbers that appear, which is what you're used to, but these questions often maybe don't allow for that. So anyway, don't be worried if the numbers don't turn out nicely. Hi there. Get out of the way. You're in the way, ghost. Okay, so this brings us to the actual problem, sort of the general part. So remember, the problem that we're trying to solve is to integrate p over q. Hopefully where p and q are arbitrary polynomials. And here's an example of the kind of generality we'd be interested in. You can see this polynomial, I won't bother reading it out. But if I ask you to integrate this, well, what are you supposed to do? Right, that's a very complicated looking problem. It certainly doesn't fall to the methods we've already just developed, right? A linear numerator, irreducible quadratic denominator. Well, that isn't like that. But look at the right-hand side. Okay, the right-hand side is easy to integrate, right? That will give me a logarithm by a substitution. That, well, that'll be 1 divided by u squared when I make a substitution. That's easy, right? That'll give me something like, well, it'll be 1 divided by u squared, that's u to the minus 2, so that'll give me a 1 over u for some u. This again will give me a logarithm. And this here, well, that's an irreducible quadratic, and that's linear, so that will be the thing we just did. I'll say above. We don't need to do it. The point here is just to see that we can, right? The right-hand side is amenable to the methods we've already developed, whereas the left-hand side does not appear to be. So it's therefore of interest that these two functions are the same. How do we know that? Well, it's easy to verify. You can just take this denominator, you can multiply it over to the right-hand side, and see that when you cancel out all the factors, you get the same thing. But that doesn't tell you how to come up with these expressions in the first place. All right, so that's the method of partial fractions that we're now going to develop. And we'll start it today, and we'll finish it next lecture. Okay, so there's several steps in this. It's a fairly complicated little algorithm. And the first part, which is the only part that I'll talk through in any detail today, is the reduction to the case when the degree of p is strictly smaller than the degree of q. All right, so let me explain why it's sufficient to handle that case. So suppose you're given a problem where the degree of p is actually larger or equal to the degree of q. Well then, by division, long division or Euclidean division, we can write p as something times q, let me call it f, plus r, where the remainder r has a degree less than the degree of p. Sorry, the degree of q. Right. That means that dividing through by q, p divided by q is f plus r divided by q. But that means the integral of p divided by q is the integral of f. That's easy because f is just a polynomial, plus the integral of r on q. Okay, but this is what I said it suffices to do, right? So it suffices to work out the integral of p on q, which is a general ratio, well, where p is greater than or equal to, in degree, to q. It suffices to do integrals of this form, which have this property. The degree of the numerator is less than the degree of the denominator. And that's what this says, right? That's the reason why that's true. if someone gives you a thing like that to integrate, your first step is to check, is the degree of the numerator too big? That is greater than or equal to the degree of the denominator. If it is, then first you get to do polynomial division. Yay. If not, then you just proceed, right? So the examples we were doing earlier were of that form, right? Linear divided by quadratic. That's a lower degree numerator than denominator. The next step. So once you've got the degree of p less than the degree of q, then factorize q. What does that mean? Well, this is the part of the course in the last 3 weeks where you start to see why all this stuff was there throughout the semester. Remember, we talked about taking a real polynomial and then thinking about it as a complex polynomial. The fundamental theorem of algebra says that any complex polynomial can be factored into linear factors. Now, some of those linear factors are just sort of on their own, and some come in complex conjugate pairs, right? So the ones that are on their own, that is, the ones that are real roots, so these are all real numbers, the a1 through aj, and the b1, the c1, the bk, the ck. When you factorize q over the complex numbers, what you see are some real, so these are from real roots, the real roots being the AIs. And then the remaining roots over the complex numbers, if you recall, came in complex conjugate pairs. Now remember what we did with those, right? We said x minus w times x minus w bar is, when you expand that out, you get something that has real coefficients, and it's an irreducible quadratic over R. That's this kind of thing, right? These quadratic factors here are the remnants of multiplying together two linear factors over R corresponding to two complex conjugate roots. So in any case, the fundamental theorem of algebra plus this observation means that Q, any real polynomial, can be factored like this into linear factors and irreducible quadratic factors. Okay, so now let's see how that gets used. Theorem. We start with the degree of p being less than the degree of q. Then factor q, so it looks like the denominator here. Right? This is a q. I should recall, the theory says that you can factor q like this, but that doesn't mean in practice you can do it. Right? It theoretically exists, this factorization, but it may be very difficult to obtain. We talked a little bit about that earlier. We're just going to not worry about that. We're assuming that you can find this factorization. The theorem says that any polynomial like this can be written as a sum like this, where for every linear factor in Q, you get a summand that looks like this, where this is what you had before, and the A1 is some number. Right? They're real constants, not polynomials. Right? So for each of these linear factors, you get something like this. For some A1 through AJ, you have to figure out what constants make it work, but the theorem says that they exist. And for every irreducible quadratic factor of Q, there exist B's and C's such that, well, when you write out the right-hand side in this form with the irreducible quadratic factor in the denominator and some linear factor in the numerator, you can find a linear factor such that when you add them all up, you get p divided by q. All right. So what's the upshot? The upshot is that the integral of p divided by q, which is the integral of that, is just the integral, or rather the sum, of all these integrals. And these we can do, right? That's a logarithm, that's a logarithm, that's a logarithm plus an arctan, that's a logarithm plus an arctan. And all of those integrals we can do from the first part of today's lecture. So that special case, linear divided by irreducible quadratic, plus integration by substitution, plus the earlier theory about factorizing q, plus long division, means we can do any integral that's of the form, in principle, any integral that's of the form, integrate a rational function. And we'll leave it at that for today. Thanks everyone, and see you in person.